So this next section is particularly important. I talked a lot about fracture mechanics because it controls the behavior of the cracks in the material. But the fact of the matter is, for the most part, we're going to be interested in how strong the material is. Will it break under a load while in service and some component? And mostly we get that information from testing the strength and analyzing the strength, and I'll show you later on, in a statistical manner. And kind of by way of outline of what I want to talk about here, first of all, I will only talk about ambient temperature fracture. Elevated temperature fracture certainly does occur under those applications, but I'm not going to cover that in this lecture. And I'm going to talk some about uniaxial flexure tests, biaxial flexure tests, and also a very little bit I'll show you direct tension tests. One slide or two slides on fiber testing, and then a fair amount of time spent on statistical analysis. And as I go through, I think you'll see why that is of particular importance and represents, in the way I'll show it, some new thinking on how we use statistical analysis to make better predictions of the reliability and the safety of ceramic materials. There's going to be no discussion of either compression or creep testing here. Creep testing can be an important aspect in high temperature applications of ceramics, but that's an indifferent topic. So this idea runs completely through the whole section and is important for every aspect of analyzing the behavior, the fracture behavior of ceramic materials. And because there's a distribution of these fracture initiating sites, quote unquote flaws, which have varying severity, the strength of brittle materials consists of a distribution in measured fracture failure strengths. That is an extremely important concept. And our goal is to determine the confidence that we can say that a particular component under a known stress will survive for a particular time. How can we do that? For ceramics and glasses, there are no non-destructive tests that can be used to distinguish one severe flaw from a whole distribution population of flaws of similar size. Unlike metallic materials, where flaws are much larger, and we can see and discriminate between the failure-producing flaw and the rest of the population, no such technique today exists for ceramics. There's another technique called proof testing, which has been used for ceramic materials, but it's complex, it's expensive, and the difficulty is you have to apply the proof test stress exactly as the component would see the stress in service, or it's not particularly effective. Give you an idea what a proof test looks like. It's the following. What the idea of a proof test is, we load up the particular component to a known stress. Those that fail during that load up are known to have flaws larger than the critical size that will cause failure in the component. They drop out, and we make the conclusion then that any remaining flaws are such that the part won't fail under the stresses that it's applied during service. But again, as I said earlier, one has to, you basically truncate. Here's a distribution of failure stresses. When I unload, when I create a proof test and unload, I really truncate that distribution. So I get rid of all the low strength failures. But you must apply the stresses in proof testing exactly as the part would see in service, and you must unload rapidly, otherwise those remaining flaws will grow slowly and cause you the same problem. So it's used, but not very often. So we're kind of left with one third option, and that is to carry out fracture testing on a subset of the entire population of components, namely specimens, and then somehow extrapolate the results from what we learn from that set of specimens to predict what happens in the components themselves. And that's the theme of the rest of the presentation in this section. So that requires a statistical analysis to determine what will be the minimum failure stress we should expect in a large number of components that we might want to produce. And in doing this, flexural tests are by far the most popular. They're the easiest to conduct. They are, because we are failing from surface flaws in the material, I can run a flexural test. It's going to fail from the same flaws that would cause failure in the component because they're going to be machined in the same way. And tensile testing, as I'll point out in just a few minutes, is difficult. Flexural testing be conducted either uniaxially on bars of material or biaxially on plates or discs of material. So either way. One of the key points, and I'll make it again later, is that for any of these, if I want to really see how the component is going to behave, the flexural test specimens must be prepared in exactly the same way as the final finish on the component. In other words, machining and polishing of flexural test specimens must mimic that of machining and polishing of components. Otherwise, my extrapolation from testing of specimens to testing of components simply will be incorrect. I would point out that there are numbers of standards. I mean, these flexural tests have been available for many years. There's a lot of data out there. There's a number of ASTM standards that are used, and quite good standards for running some of these tests. I don't feel any need to go into detail. Those of you who are going to run a test, I strongly encourage to go look at the standard itself. The details of how one does the test can be extremely important to the accuracy of what you're doing. And again, the ability to have a standard for a flexural test is a big cost reduction method. The machining houses, if you have a new material and you need to do some flexural testing and need specimens cut, it has become much less expensive to get your specimens made because they're all made to the same specifications. The size of the specimen, the size of the fixtures have been standardized, and so getting exactly the specimen you want at a relatively low cost has become significantly lower in recent years due to the standardization. There is, however, a very nice publication by George Quinn and Roger Morrell on a review of the flexural test, and it'll give you a lot of detail on the whys and wherefores of how the test is done, why it's done in that way, and so forth. It doesn't go into the same detail as standards, but it's a very useful kind of reference to look at to get a further idea of good practice in flexural testing. So here's what a uniaxial flexural test looks like, taken from their reference. You can be in three-point bending. In other words, I have a central load that you see here. It's supported on two ends, and I simply load it to failure. And there's a couple of different ways, what are called quarter-point loading that you see here, or third-point loading that you see down here. These are common in the standards, but basically they're loaded at 2 points, and the maximum stress, rather than being concentrated at a single point that you see, is spread out over this length of the particular flexural bar. That's important because you obviously get much better statistics by doing 4-point bending than 3-point bending, and part of the advice that I will continue to say over the course of this lecture and probably others is that if at all possible, do a 4-point bend test. But there are other concerns by 4-point bending. You've got to be careful how you support the edges. You've got to be careful there's no friction at the loading points and so forth and so on. But this is a very nice schematic of how the test is done. And kind of a few things of advice. I mentioned, when possible, use 4-point flexure rather than 3-point flexure. I mentioned before, there are commercial establishments who will machine specimens to standard specifications for you. I can give you their names, or you can find them in other places, but I think that's important. Here's an important point. If you want data that doesn't represent failure from edges, because edges have sharp corners on them, they typically can get damaged more easily, and if they're there, the likelihood is you will get failure from an edge or a corner rather than from the rest of the specimen. If you don't want to look at that as part of your component, then you have to either round that edge or chamfer it on the tensile side in order to avoid those kind of edge failures. And you have to use what is called an articulating load system to avoid errors due to friction and unwanted bending, particularly at the loading point. So these are just general pieces of advice. And again, I don't have to go into detail because when you go to the test, you'll go to the standard. It will tell you exactly the same thing. It will explain what kind of loading fixture you need, and strongly advise that you follow the instructions in that particular standard. That's uniaxial. Biaxial flexure tests have also been. Roger Morrell at the National Physical Laboratory in England wrote a very nice, what's called there, a good practice guide for flexural testing. And again, I strongly encourage you go look at that because it's easily obtainable on the web. So that's a very useful way to get more detail. There are numbers of kinds of biaxial flexure test configurations. You see here what are called ball on ring, a ring on ring test, a piston on ring, a piston on 3 balls. All of these have been used, some all more or less extensively, depending on the shape of the specimen. And you can use either discs or plates here. The thickness of the plate is important relative to the extent of it. Otherwise, you get wedging action or unwanted stresses develop. But thin plates or thin discs work very nicely. And it's hard to, there are considerations to think about. The one that's tested a fair amount, a ball with a flat on a 3-ball test is easy. In other words, you put a ball in the center, but the area under the stress under that center ball is small, and the analysis of the stress state is accurate, and you don't have to worry about overhang. So that's important. People always ask that question, do you worry about the overhang of material? And that seems to make a very minute difference to the analysis of the strength of the material. Ring-on-ring tests interrogate more material because there's a larger area of your disc or plate under stress in those tests, but the alignment of the particular test is a little more difficult. And the choice will be what kind of equipment you have, how accurate do you need the material to be, how big of plates are we talking about. But this gives you a flavor then between 2 kinds of tests on what sort of procedure you should use. I need to talk briefly and very briefly about direct tensile tests. Can be very complex, and you should only use them where there's some possibility of failure initiating from an internal defect, namely a pore, an inclusion, something else in the inside of the material that's a more severe or lead to a more severe flaw than the machining that we normally think of as causing failure. And there are, when I say numerous, this figure shows only a few of the kind of designs of tensile tests that have been used. In case of the use for components that are going to be used at elevated temperatures, which is typically where we might want to have direct tension experiments because the component itself experiences stress states which put a lot of stress in the inside, or the way I made the specimen can induce pores or inclusions, you're going to have to go to a tensile test, but they're beyond the scope of discussion here. So there's some key points to consider in tensile tests, what's really important, and just to try and point out, you've got to avoid failure from stresses under the grips. This is always a difficult proposition, so these have been discussed in a number of references that I'll talk about at the end. Misalignment is a key issue in tensile tests, and to avoid undue bending. If you produce undetermined bending stresses, you can cause significant errors. And the environment is particularly important if slow crack growth can occur. So tensile tests in the environment, if you're doing this at high temperature, you've got to do the tests themselves at high temperature. As I say, elevated temperature tests, I'm not going to talk about the failure mechanisms at high temperature. They become quite different than what we see in ambient temperatures, but the gripping becomes more difficult when you're testing at high temperatures, and you've got to be careful to keep the grips out of the hot zone. And so there's a reference, reasonably old now, but it gives some feeling about the behavior of materials to a couple of different chapters in this. I said I wouldn't talk about creep, but the creep involves some of the designs for tensile gripping, so I leave it in here. So, again, there's a lot of detail on this that we can't cover in this course right now. I mentioned the idea of fiber testing. The manufacturer of glass fibers for optical communication is always concerned about the possibility of glass fiber failure. And one of the ways the strength of those fibers are tested is to pull them continuously as they're drawn out of the melting furnace in a take-up mandrel that rotates faster than supply mandrel, so they're naturally strained as they come across. It's more or less a proof test. If it fails, then we know that there's a low-strength region is there. But you can also test fibers in direct tension. One of the interesting one is what is called this two-point fiber test, where you bend the fiber within a constrained cavity, such as you see here. And this is a good reference to how one calculates the strain in the point of the fiber down in here, and can give you some idea then of the fracture strength of that fiber. There are other kinds of tests as well, depending on what you're manufacturing. If you're manufacturing rings, things like C-tests or O-ring tests work quite well, because if you're manufacturing pipes, you can slice out rings or circular sections from your pipe and test in this way. What is called diametric compression has been used for years by the concrete people. It's simply a diameter of a material in which you test in compression, and it turns out the material actually fails in tension from the end of the specimen that you see here. So again, these are valuable tests for both tubes and rods. So all very interesting. And I show here, and I won't go into it, there's a number of summaries of the useful tests and some more references to where to find the data for that. The next section I think is particularly important, and one I want to focus on a bit, and hopefully maybe I'll get some feedback from some of you of how useful it was. But I think it's the most important part of the testing procedure, and that is, how do we analyze the statistics of failure from a small set of specimens to be able to understand and have confidence in the strength of my set of components. So schematically, what I'm really doing is, if I'm looking at the frequency of failure on the ordinate here as a function of flaw severity, I'm taking, if I look at simply the section in red, I'm taking a very small section of flaw severities out of a much larger section of potential flaw severities that might exist in my components. And hopefully by doing this set of measurements, I predict what happens out here. And that's what I want to run through in the next few set of slides. So what are the requirements that I must have in order for that approach to work properly, namely that I can make that kind of prediction? First of all, I mentioned earlier, all of my specimens must be manufactured and finished exactly like the components. And this is kind of difficult to always guarantee, that no flaws are created during use. I'm going to predict the lowest possible strength of my component, but I will always assume that I don't damage it in some way. That may not always be possible, but you know that that condition is there and you have to be aware of it. And I think many of you, or all of you who have ever dealt with statistical failure of ceramics, work with what is called a Weibull distribution. This is a distribution, it's a statistical distribution that has been used for years based on what has been called weakest length theory, namely the idea being that the most severe in the material causes failure, and so once that happens, the rest of the flaws are no longer applicable. So it fails from that one flaw, and it's a probability distribution. I will say now that it's not the only distribution, and I will show in just a few minutes this particular equation may not be the best distribution to fit your data. But this simply represents that the probability of failure is a function of the fracture stress that you see here. There's a scale parameter, sigma 0, and what's called the Weibull modulus, the exponent on this distribution you see here. And this is a number that can range from 2 to 30 or 40. And the smaller the number, the wider the distribution of failure stresses. And this is shown integrated over the entire volume of the material, but the exact same equation would work if we simply integrated over the total area of the material under stress. In other words, it works in exactly the same way as I show down here. So this equation, or a similar equation to it, I'll show in a few minutes, is the one that is typically used to explain statistics of failure of brittle materials. So how do we plot our data? We have this whole set of data we've now determined. We can range it from lowest to highest. Typically, I'll show you in a moment, 30 tests are recommended in the standards, but that really is just a unfirm number. It's not based on any real absolute value that we have to have. If it will be determined by how accurate you want the prediction to be. The more specimens you test, obviously the better number you're going to get. How difficult it is, how expensive it is to do the tests, what the distribution in data looks like. All of these things have to be taken into account. There's an ASTM standard for plotting the data. It's 1239. So this tells you how to plot your data. It uses what is called a maximum likelihood technique. Again, I'm not going to go into the mathematics of what this technique represents, but it's pretty easy to put in practice for the determination of fracture stress for brittle materials. And I'm going to stick with this technique, although there are other fitting techniques that are available as well. And then when you plot the data, you will get a line. I've showed this kind of before, where you're plotting the probability of failure as a function of applied stress. One of the points I want to make here is that it's important to know not just the probability of failure, but why failure occurred. And you see here things don't follow the same curve throughout the entire strain range or stress range. And so down at the low stress regime, there is a change in the slope of the curve, and George Quinn, who collected this data and did all of the detailed fractographic analysis, and I'll stress this later on when I talk about fractographic analysis, it's really important to know from what kind of flaw source did failure occur. So the sources of flaws or the sources of failure down in here will not be in this regime. We care a lot more, as you might imagine, about the low strength regime than we will about the high strength regime for almost any application you can think of, because we're worried about failure in a component. We care what the lowest strength is, not necessarily what the highest strength is. So I encourage you, and I'll say it again later on, to look at the source of failure wherever possible to understand what might happen. So this represents something like a bimodal failure source, that these failure sources don't look like these for whatever reason, and that's going to be important. The area under stress is important. As you might imagine, the greater the area under stress, the lower the strength will be the material, because the probability of finding a larger flaw is going to be particularly susceptible to that. Let me go back. I want to go back to that equation again. So you can see then what I'm doing is integrating either over a larger volume or a larger area, and that will make a difference in the probability of failure. So you can see right away from that expression why that is particularly important. You can also see that the kind of test geometry, I showed you different ways of doing testing, will make a difference. You can see here different kinds of test geometry used to predict strength and probability of failure for a whole bunch of materials. That will also be important. So be aware that you test in one way, you will get one distribution of strengths. So you want to test with a test procedure that closely mimics the kind of shape of component that you're going to be looking at. As I said earlier, if you're going to be manufacturing pipes or ceramic pipes, then test so that the stresses in the pipe can be measured directly in your test in the laboratory. And then how do I get to the strength distribution in the component itself? So again, I sort of said earlier, you've got to account for the greater probability of a failure-producing flaw in the large set of components compared to the set of specimens you test. And in that equation that I showed earlier, the strength is assumed to scale inversely with the area or volume of stress according to the following, namely, as I increase the area with an exponent of 1 over that Weibull parameter m, the strength will decrease accordingly. So it's inversely related to the area under stress to the 1 over m power. However, that's only useful if I look at two-parameter Weibull expressions, and I'm going to show you in a minute that we now think that that's probably not the best way to analyze strength behavior. This method is only valid for two-parameter Weibull expressions. So let me give you what I believe and is a newer approach to predicting probability of failure. First of all, it's not necessary to assume that that earlier expression for Weibull is the best one to fit the data. It's only one of many. You can try any probability function you like to fit your data and calculate how well that data fit is achieved with that expression. There is nothing, this may be somewhat controversial, there's nothing fundamental about Weibull. There are lots of expressions that fit data. They're all statistical expressions, probability expressions, and this concept of weakest link theory is not terribly useful to understanding or using to predict failure of brittle materials. But having said that, one expression that Weibull did develop does work significantly better, namely what is called a three-parameter Weibull equation, where this now the other parameter that wasn't present before is known as the location parameter, or the lower limit to the strength distribution. If you recall, if we don't look at this expression that contains the minimum strength, then there's a probability of failure at zero stress. In most minds, that is extremely unlikely. It makes the two-parameter Weibull extremely conservative and probably unlikely, maybe too conservative for a designer. In other words, if you allow failure at zero stress, you're going to be over-designing components. So at least if you're going to use different expressions than two-parameter Weibull, the three-parameter Weibull is a very nice way to look at that with this so-called location parameter, because this is really the parameter that we want to know. What's the minimum possible strength in my set of specimens that I have, and then ultimately in the set of components that I'm going to create from it. So if you look, I did this as a function of steps. So the first step was to choose the function that you see here. The second step is to fit the function to the data. I said earlier, the maximum likelihood, again, all of these, if you go to statisticians, they'll tell you there are other ways to estimate the best fit of these functions. But if you want a good fit, and you can determine the uncertainty balance in that fit, namely 95% confidence limits, then maximum likelihood works quite well. The next part of it is very new. You remember earlier I talked about using the area or volume under stress as a measure of predicting the lower strength or the strength of components. And that seems to go in the right direction, but a more modern approach is to use these concepts of tolerance limit and coverage to determine the probability of failure of populations of parts. And a very nice reference is a book by Nelson, Coffin, and Copeland on statistics for engineering that goes into what these things mean, but I'm going to show briefly what they mean and how they're applicable to this would work for not just brittle fracture, but for other applications of statistics as well. But I want to go briefly into what these things mean. So first of all, what we want when we do a statistical analysis of strength is to have some confidence on the data that we're determining. So for a specimen population, this is just simple statistics. The confidence limit on the mean of that distribution is given by an expression right here, where this would be a student's t-distribution, SD is the standard deviation, n is the number of specimens. And the lower limit to that mean then would be the average S sub 0 minus D1. And I can show that on a schematic like this. If I take 10 numbers representing 10 tensile strengths of a material, you can see here what D1, this we've plotted as a normal distribution, but the D1, around the mean of the distribution, is shown here. So D1 is 12.6. So you can see where the breadth of that distribution is. But that only represents one point. It does not represent the lower limit to the distribution itself. It's not the parameter we're really going to need. So here are the other important parameters in the statistical analysis of this set of specimens. This number D2 is known as a prediction interval. If I were to test one more specimen, it gives me some prediction of where that single future observation of strength is likely to be. But the real number I want is known as D3, the tolerance interval, and indicates the strength level where a large proportion of the entire population of components, of things I make, of components that look exactly like these specimens, is likely to be. And these numbers are relatively easy to calculate if all my distributions were normal distributions that I just showed in the example. One can go to tables in the literature in this reference I showed earlier, and the values of those numbers can be obtained. And the numbers I'm talking about here are these numbers, not just the standard deviation, but gamma, which is dependent on the extent of coverage. What do I mean by coverage? It means, do I care whether I'm 90% safe, whether 90% of my components are going to be safe above a certain stress level, 99%, 99.9%, etc. That number comes directly out of the tables. And mu is also a number determined by the number of specimens I test and also the level of confidence in the number D3 that I want to see. So showing this on the same kind of graph I showed before, here is, for this sample size of 10 specimens, a mean of 100 megapascals and a standard deviation of 20 megapascals. The D1 that you saw earlier is in here. Here are the D2 limits, and I'll say here, in the real world, I'm not really going to care about this upper limit. I really care about what the distribution looks like at the lower end of the strength scale. So in that case, I really want D3, which is the tolerance limits, the limits in population space. In other words, for the entire set of components that I might be manufacturing, D2 represents only the distribution in the sample space, that which I test. And you can see here, if I want 90% confidence limits, the D3 is 56.8 megapascals. In other words, I reduce the mean in the set of specimens, the lower limit of that set of specimens, by something of the order of 57 megapascals. So the lower limit to strength is here. That's the lower limit, what I should expect in my entire set of components. For 99% coverage, if I want to be even more safe, then I have reduced the stress by 88.7 megapascals. In other words, there's a probability or a possibility of failure, I'll say possibility of failure, at less than something like 12 or 13 megapascals. But this gives me the confidence level that I need to be sure on my entire set of specimens where I should be designing. And if I wanted to reduce the set of these numbers, I can test more specimens. This will, by nature, reduce the sizes of all of these numbers. I can reduce my desire to have absolute certainty by use 90% confidence levels. It's up to the individual, but the data is there, and the statistical analysis is there to get you to the point where you have some confidence in the number that you predict. So let's say let's put it another way. The lowest tolerance limit, the lower strength limit in this set of distribution at a 90%, 95% confidence level. In other words, let me point out again, this is not an absolute number. There is a confidence band about this number as well. And so with 95% confidence, I can say that the lowest limit to the strength in a set of components of this nature will be at this level. And I just point out this is all very new. There's a new publication that will be in the NIST Journal of Research to be published by the end of this calendar year 2017, that I think gives a lot more detail on how this analysis is carried out. So let me just summarize briefly that on the idea of strength measurements, that you select your strength measurement technique based on the shape of the material available and the type of information needed and the availability of testing equipment. It all seems very obvious, but it really helps in determining how you do the test and how good your data will be. We've tried to show that there's a new three-step statistical approach to determining probabilities of failure, and these use this concept of tolerance limit and coverage to determine failure probability, which is really what I want to know. I need to know the lowest limit of the stress or the strength of the component in that particular application.